problem. I'm making a video and audio filing. This is 790 Domino and Tromino tiling. You have two types of tiles, a 2x1 domino shape and a Tromino shape. You may rotate these shapes. Okay, so you have this domino shape like this. Of course, the idea is you can rotate this little guy, right? So even though the shape is like this, it could also be oriented like so. And then you have this Tromino complicated shape that can be rotated, 4 ways. You could have it like that. You could have it like this. You could have it like this. What am I missing here? And you could have it like this, right? So these are the 4 ways that you could have a Tromino, right? So there's really 4, 5, 6 different shapes if you want to think about it in terms of like the grid cells that they occupy, right? Of course, these bottom 4 shapes are created from this Tromino, and these top 2 shapes are created from the Domino. Okay. Given an integer n, return the number of ways to tile a 2 by n board. Since the answer may be very large, return it modulo 10 to the 9 plus 7. Okay. In a tiling, every square must be covered by a tile. 2 tilings are different if and only if there are 2 4 directionally adjacent cells on the board such that exactly one of these tilings has both squares occupied by a tile. Okay, so essentially all that's saying is we basically want to have a grid. Like we're going to have this grid. So for example, 1, when n equals 3, that's basically saying you have this grid like so, and it has length 3. And we just want to know how many unique ways can you populate this grid with every cell filled so there's no holes, such that each orientation is unique. What's the total number of ways that you can do that, right? So for example, I could put I could put one of the horizontal tilings here and another horizontal tiling here and a vertical tiling here. So that's one way, right? I could put 2 vertical tilings here. I could put 3, I guess. I could put 3 tilings here. I could put 2 on the other side horizontally and put a vertical tiling here. Right. And that's everything, just exhausting these 2x1 pieces, sorry. And then finally, right, I could use these Trominos by kind of attaching them like this. Right. And, oh, what am I doing? I'm not drawing a gun. All right, like that, and like this. Excuse that sloppy drawing. But so those are 5 ways, right? So there's 5 ways to take this 3 system, right, this initial blue grid, and populate it with Tromino and Domino pieces. So it seems simple enough. Now this problem seems very confusing, right? Because this Tromino piece is like so strangely shaped. I think the most intuitive thing, right, would be dynamic programming, because we're talking about total number of orientations, right? Because like what's really happening is, if you thought about this in terms of, dynamic programming, you see subproblems here, right? There's an n equals 2 subproblem. It's a different color. There's an n equals 2 subproblem here, right? What I'm saying is like, I can attach a piece like this, right, at the nth value, and then there's a system. There's an n-1 system that we've already solved for, that we can attach ourselves to, and it'll still work. That's already completed. So what I'm saying is for n equals 2, right, that what I'm trying to get at essentially is like, for n equals 2, the ways that you can do it are these 2 systems, right? For n equals 2, you have dominoes, 2 dominoes like this. or you have two dominoes like this. So then when you have n equals 3, well, then I can just attach the third domino to the tooth case, right? So I can attach this new domino to each of the two cases, right? So in the two cases, I have these things here. So for n equals 3, I can take the two cases and I can attach a domino like so. I can attach my domino here and I can attach it here, right? So I get two more cases that way. Now, of course, those aren't the only cases, but you can see how this kind of works, right? For n equals 3, I can take the n equal 2 cases and attach this domino, right? So in any generic example, if I have the nth domino, I can attach it to the n minus 1 set of dominoes if I put it in this orientation, right? But there's multiple orientations for this domino, right? The other one is, well, you know, so I guess what we see here, right? If we want to say so far, what we see is for the nth case, we can always attach ourselves to the nth minus 1 case, right? So this is kind of one system, right? If I wanted to talk about this dynamic programming problem, if I want to talk about this dynamic programming problem in terms of the previous iteration, right? Well, if I called it I'll call it full, just F or full of n, right? Well, for full of n, let's erase this stuff. I'm going to get full of n equals full of n minus 1 plus something. We're going to determine what that is, right? Because this right here is full of n minus 1. Right? That's what this yellow system represents. So this is basically saying this corresponds to adding one of these babies as the nth one to one of these, a full system here, which is n minus 1. The nth minus 1 system here. So that's what this basically is saying here. So the number that I can get at n, well, I can just attach a vertical one, and then I can get the total number that I would get at n minus 1, right? Which happened in the 3 case, right? When I attached a 3, I could get all the ones from 2, right? And the ones in 2 are this, the horizontal one stacked on each other and the vertical one side by side. So that's basically the idea of using dynamic programming, right? What I can get here, well, I can attach this thing so then I can just add in everything that I can get before. But of course, that isn't the only thing that I can do. What I can also do is, well, what is n equals 1? Well, n equals 1 equals just this. The only thing you could do is put a vertical system, like so, right? Because n equals 1 means that it's a, you know, the length is 1, so the only thing that you could put there is a 2 by 1. Right, and you'll see n equals 1 here in this system. Right, so I can always attach 2 grid cells like so two on top of each other like this. If this is the nth index, well then now I can't use the solution at the n minus 1 because I just placed these tiles here, but I can use the solution at n equals n minus 2. Right, so I can get the solution from n minus 1, and I can also get a solution at n minus 2, right? Because I would just attach side by side, stacked on top of each other for the solution that's n minus 2 to the left, right? Whatever the complete solution is here, well, I can just attach myself to that, right? So then we also have full of n minus 2. Now, this would be the entire problem if there wasn't Tromino pieces, right? The Tromino pieces kind of complicate things because it's no longer just, you know, a domino like this or a domino like this. There's this weird idea of holes. But you see this so far, but this isn't it, right? Because we haven't even considered the additional pieces. But I'm hoping that at this point, you at least understand the dynamic programming aspect of this problem, right? You've already got the whole full system for n-2. So you already have that whole full system. So I'll just attach 2 dominoes stacked on top of each other, and that'll give me a whole new set of solutions, right? Where it's all the ones that I got before attached to this one, plus all the ones I got before up until n-1, attaching a new vertical domino, right? And doing that alone, you capture, you know, these 3 solutions. These 3 solutions are already captured with this one, right? Because this is n, and this would be n-1. So you would add in f of n-1, right, to get these 2 solutions here. And then you'd add in f of n-2 to get this solution here. Right, so for f of 3, you can just use f of n-1, f of 2, and you'd get these 2. And then you do f of n-2, which is this one, to get this one. And so we just have to account for this idea of these trominos and what that does to our solution. Okay. Well, you know, this comes down to, what if we added a vertical domino? What if we added horizontal dominoes? Well, what would happen if we wanted to add a domino like so? Right, because what we're trying to do is we're trying to fill out the last node, right? Because we want to make it full. So in order to make it full, the nth column, right, has to be full. So it has to be covered. So this is one way to cover it. But the problem is this isn't n-1, because this piece is already covered here. So we can't have overlap, right? They can't overlap each other. So it's not full of n-1. It's also not full of n-2, because if it was full of n-2, then this piece would be missing. So what it needs to be based on is something slightly different, right? Which is, we need the top to be empty in the previous solution, right? We need a solution where there's something missing at the top so that we can attach our piece, right? We need a piece where it's like, it's stacked up like this. That way I can put in a piece that's shaped like this, right? That way they can fit into each other, right? So the only way I can add this Tromino piece to fill out the end is if I have to find the number of solutions where there's n-1 where the top piece is missing. So we'll call this, what should we call it? We'll just call it top missing, I guess. It's fine. Top missing. So this would be top missing n-1. So this is n-1 here, right? So we'll call this top missing n-1. So that means that we can add in this top missing case. Let's delete this stuff. So we have a little bit more space here, because real estate is important. So we can add in the top missing part of n-1 if we attach this piece to fill it up. So let's do that. But that means now we have a new thing that we're going to need to account for somehow. So this is top missing n-1. And then what's the last way that you could fill it out? Well, let's look at our original pieces, right? So this one fills it out. 2 of these stacked fill it out. This fills it out. We just did that one. And this one fills it out, right? If we try to attach this piece at the end, there'd be an empty spot. If we attach this piece at the end, we get an empty spot. But, you know, that will become important in a moment. Okay. So the last way we can think about this is, well, we can add the one remaining piece that fills it out, right? We can add a piece like this at the end. Right, so at the nth system, it's all full now, right? The nth column is full, we're covering it. But that would mean that it would need to attach to a system where the bottom was missing. Sorry, it's so confusing. Right, because I need a piece where there's nothing here. That way I can, you know, push in my new piece into this slot and fill it up. right? So I need the bottom missing at this case. And of course, this is still n minus 1. So the final example then would be, oh, I guess would be that it's the final piece would then be that the bottom is missing at n minus 1. At n minus 1. So this is the whole recurrence relationship, right? The way I can fill it up here is I can put a vertical one, and then that would mean that it's all the systems that are full up into n minus 1. I could put 2 horizontal ones, so that's all the full system at n minus 2. Or I could put one of the Tromino pieces like this, but that means I have to keep track of the top missing at n minus 1. And then I could put a L-shaped piece backwards like this, but that means the bottom piece is n minus 1. And of course, we don't add these new ones like this because, this wouldn't fill up the system because there'd be an empty spot here. But then what does that mean in terms of what we need to find? Well, now we need to find top missing and bottom missing, right? Because the issue is now is, well, if I need full in terms of top missing and bottom missing, I need to know what top missing and bottom missing are. So what are the ways that how many solutions can I make it such that there's top missing at n? So now that just kind of adds another thing that we're going to need to calculate. Okay, so how do we find top missing at n? Well, how would we get a top missing? So a top could be missing if I put a piece on the bottom, like so, and there's a previous system like so, right? Because you can see here there's obviously a top missing here. So in terms of the systems, what would that be? Well, that would be a bottom, right? So this is n. And then what is this piece? This piece is just the bottom missing, right? This is n minus 1 bottom missing. So we'll call that bottom missing of n minus 1. Okay? How else could I get a top missing? I could get a top missing if I put one of these backward L shapes. Right, if I put a backward L shape, you'll notice that the top is missing. But then I need this whole system to be full. So if this is n, this would be what? This would be full of n minus 2. So that's full of n minus 2. Is there any other way to get a top missing? I don't think so, no. Okay, so then let's figure out what bottom missing is in terms of previous thing. So bottom missing equals, well, to get the bottom missing, I could put, let's move this over so it's cleaner. To get a bottom missing, I could put a piece at the top. But there's just one bottom missing, so then I would need to attach it to something where the top's missing. And then you'll notice here that, obviously the bottom's missing. So that's for the nth one. So I think you're starting to see where this is going, so I'll kind of go through this quicker. So this is where the top is missing. Or I can add a piece like this to get the bottom missing again. And then that's just the same thing. That's full of n minus 2. And that's kind of it. Right now I have everything in terms of everything else. Right? I know how to find full. right? I know how to find full because full is just based on, well, if I wanted to fill out an n, I'm going to have to put pieces at the end. What are the pieces that I could put at the end to fill it out? Meaning that I cover the last column. Well, I could cover the last column like this. I could cover the last column like this. I could cover the last column like this. Or I could cover the last column like this. If I cover the last column like that, well then if I cover the last column like this, it's based on the full system at the previous n value. If I cover the whole system like this, it's based on the it's based on the full system at the n minus 2 values because I filled out the last two. If I do it like this, well then there has to be a top missing in order for me to attach this piece. And then if I want to attach a piece like this, it fills out the last column, fills out the last column. I need to attach it somewhere where the bottom is missing. Well, then that means that I need to figure out what the top missing and the bottom missing are, right? What's the top missing for this? Well, I can create a top missing by attaching a horizontal piece at the bottom to a system where the bottom is missing, or I can attach a backwards L-shaped to a full system, and now the top is missing. Same situation here with the bottom missing, okay? So these are just our recurrence relationships, so we can just run through this system and we should be able to find the solution. So let's go ahead and do that. So this is just a classic dynamic programming problem with just, some trickery. So let's see what we can do to make this work. Okay, so we'll have full, we'll have top missing, and we'll have bottom missing, all right? I'm just gonna call them this so it's a little bit easier for me to figure out how it works. So I'm trying to think about what so full of 0 is anything, I'm trying to think of what's based on what. So full is based on n minus 2, so we should start at 2. Full of 1 is 1. Full of 0 is 1. Top missing is only ever based on top missing before. Top missing of 1 is 0. I'm trying to think about, okay, so if you had I'm trying to think about the base case, right? Because when you do a recurrence relationship, you need an initial value to start propagating forward, right? So what's the base case? If I had a system that looked like this, how many ways can I make the top missing? 0, right? Because there's no way, I can't since the system's like this, I can't attach a piece like this. Right? I'm saying that this blue system is the grid, right? It's a one system. So I can't attach a piece like that, right? The only thing I can do is fill it up by putting a piece in here, like just one vertical domino. But I can't make the top missing, so that would mean that the value there is 0. So for full, 0 is 1, and 1 is 1. For top, 1 is 0, and for bottom, 1 is also 0, right? Because there's no way that you can make a bottom empty with just one grid cell, because how are you going to put something in there? So then what we can do is we can look at each value I in range. So we've already populated 0, 1, and 2. So 2 and n plus 1, because we want to look at all n values. And we'd say, okay, now we just run through this recurrence relationship. So full of n equals full of n minus 1, n minus 2, top missing n minus 1, bottom missing n minus 1. Okay, so full of I equals full of I minus 1 plus full of I minus 2 plus top missing I minus 1 plus bottom missing I minus 1. And then we just need to populate top missing of I minus 1 and bottom missing of I minus 1. So top missing of I equals bottom missing n minus 1, full n minus 2. Okay. So top missing of I equals bottom missing I minus 1 plus full of I minus 2. Bottom missing of I equals top missing of I minus 1 plus full I minus 2. Now, this doesn't make sense, right? The thing is, sometimes the best way to approach these problems, at least for me, is to separate the logic from the code in terms of what things mean. So I've already convinced myself of these recurrence relationships. So now it's just about, robotically taking it and putting it into the code and not really thinking about it too much, because I don't want to be thinking about the logic of what I'm doing
in terms of like the complexity of the recurrence relationship while I'm writing the code. I just want to focus on making the code work using what I wrote, right? I'm just translating. I'm translating my ideas into code. I'm not thinking of my ideas as I code, right? I'm just translating. So bottom missing of n, n minus 1, top missing, full, n minus 2. But, you know, of course, you have to do a little bit of thinking because you have to think about base cases and stuff like that. So then at the end, we would just return what's full at n. And we cry because it's wrong. No, I'm joking. All right. So we'll try to submit that, see what happens. And I forgot to mod it by 10 to the 9 plus 7. That's my very common error. Okay, cool. So this is pretty much good, right? One thing we can fix is that you'll notice, right, that this system is only based on 2 previous things, right? F of I minus 1, F of I minus 2, T of I minus 1, B of I minus 1. This is only based on 2 previous things. This is only based on 2 previous things. The idea is like, we don't need to keep track of the whole system. We just need to keep track of the whole system up to the previous 2 things, right? We just need to keep track of the total number of things we can do up to the 2 previous things. We don't need to keep track of everything we've ever done for the whole system. It's kind of a waste of memory. So what I'm going to do is I'm going to convert these things just into single constants that we update and then return. And the idea is that we can just update those constants and we don't need to keep track of everything we've ever done to take the runtime from O of n down to O of 1 or constant. Okay. But in order to do that, I'm just basically going to force replace all of the variables and hope that it works. That's usually the easiest way of doing this. You write it in O of n and then you figure out, okay, this becomes the, like you just replace variables and it'll get you to O to 1, right? So I'll have what F was previously, and then I just keep track of top and keep track of B. So F previously would be 1, F would be 1, T starts at 0, and since the value here is 0, then B also starts at 0. And then I just update these things accordingly. So F becomes what F was before, plus what F was before that, plus what T was, plus what B was. T becomes what B was before, and what F was 2 times before. B becomes what T was before, plus what FF was before. Now, of course, now all these variables need to be updated at the same time. And of course, you want to take FF and set it to what FF was before after you're done, so that the next iteration has access to that information. So then in order to make this work, we need to put it all on one line, or we could do a series of swaps that I'm not interested in doing. Okay. This is a very risky way of programming because I'm basically just saying, these are the things that I'm trying to do to make this work, and it's confusing, right? But it's constant time, and I've already written a solution that isn't confusing, so maybe, you know, you'll get some leniency. It's not going to work because it's, yeah. I've attempted too soon. Cool. All right, there you go. 3-line solution. So what is this in terms of space and runtime complexity? All right, well, let's say that n is n. Okay, good. So time, well, we populate these 4 variables, right? That's constant time. And then we just have to look at all n. We have to look at all n columns in order to update them. And for all n columns, we just do something constant, right? We update this variable, we add these things together, whatever. And at the end, we just mod it 10 to the 9 plus 7. So no operation would ever get bigger than 10 to the 9 plus 7. So that's a constant operation in terms of 10 to the 9 plus 7. So it's for n things, we do something constant. So we do n constant things. So that's n times constant, O of n. All right. And then before our space, when it was easier to read, was n space, right? Because we had to keep track of each column. But since we only need to keep track of the 2 previous columns, we just have these 4 variables, and then we update these 4 variables accordingly. We never have to deal with anything else. So even if there's 10 million variables, or if n is 10 million, or n is 1, or n is 400,000, we only have to keep track of these 4 variables. So it's constant space. All right, guys, fun problem. I skipped this one a few times. I'm glad I came back and really just walked through how this is supposed to work. Never a bad idea to go back to problems you couldn't solve before, because who knows? Maybe your skills have improved, or maybe you're just having a better day and you got better sleep. I don't know. Peace out.